Hello and welcome back to the Bioscience Python tutorials. Since the last time I went through, commented my code, obviously go through, comment your code because you're going to look back on this in a little while and you're going to forget whatever you were doing here. So go through, write some comments. But today we're going to get through the real meat of this, the really cool part. We're going to implement the Needleman-Wunsch alignment algorithm. And so now it's time to start defining our alignment model. So I've decided to implement this in a way where we're only going to take in a scoring matrix, and then we're going to be able to get an alignment for any sequences that we input um, for that scoring matrix. We're going to have to use that scoring matrix, though, in any case, for whatever alignment model we create. And the way that these methods are going to work together is that get alignment is actually going to take in a sequence and another sequence. Um, we're going to have to initialize our model with our scoring matrix. Our alignment helper is going to set our model's scoring matrix, or it's going to help our alignment actually return a string representation of the alignment by getting the scoring matrix. So we still need to input a sequence in sequence 2 for the alignment helper. And then for the Needleman-Wunsch algorithm, we're going to take in our two sequences as well. And this is just going to be like a separate tool. And so the alignment helper is going to be important because it's going to allow us to actually to get the scoring matrix from our Needleman-Wunsch algorithm, and we're not going to have to do that in our alignment method because we're going to want to actually run Needleman-Wunsch separately sometimes. So because that's going to be how we actually determine our alignment significance later on. So for now though, let's just start implementing this. Let's get down to brass tacks about this. So for scoring matrix, the way you set these variables that are persistent within your model in Python is you're going to say self dot scoring matrix. You can name this whatever you want, but I'm going to name it scoring matrix because that's the most intuitive name for me, and that's the only persistent data that I am going to keep within my model. Okay, so let's just try initializing our model with our scoring matrix. Let's say uh, alignment equals, actually let's just call it align. Align equals alignment with Blossom, and that's going to be our scoring matrix implementation. So it's giving us some errors, but we'll be fine. Yeah, align worked successfully. So let's just go through and make that a little bit more obvious. Let's say print self scoring matrix dot keys. Cool. Great. So these are all the keys, these are all amino acids, but it definitely demonstrates that this data is saved within our alignment model now. Okay, so that's really great. Now that we have our scoring matrix, we want to get an alignment for specific keys. I guess it's worth mentioning that we actually need to define a gap size here. So we're gap cost. Okay, so gap cost in this is going to also be a predefined thing for our model. So we're going to say self.gap cost equals gap cost. Great. And we're going to go back and we're actually going to set that here as -8. And that might seem steep, but it's because protein changes are much more significant than DNA base changes. So now we're going to go through and we're actually going to implement Needleman-Wunsch first. Our get alignment method is just going to call some other stuff and it's going to backtrack through our Needleman-Wunsch matrix or our scoring or our scored matrix, our dynamic programming problem solution, and it's going to tell us the sequence by backtracking through that. but the Needleman-Wunsch is the thing that's actually going to give us our scoring matrix. So we're going to begin implementing it as soon as possible. First things first is we saw back in here, we saw that we want to initialize our matrix with all of our gap costs because this is going to set a boundary and it's going to be able to build further, and further down into this matrix as we progress through the algorithm. So first things first, define our matrix as the size of our two sequences. So we're going to say M equals length of self.sequence, sequence 1, and N equals length of self.sequence 2. And Python's going to yell at you because you're not supposed to use capitals for variable name starts, but we don't care because that's what I want to do for scientific notation. So now we're going to make our problem matrix. So we're going to say our actual alignment matrix equals, we're actually going to have to import a tool for this. We're going to have to import from, I'm going to say import numpy as np. Okay, and if you don't have numpy, just go and do a pip install on that. If you have Python 3, just do pip 3 install. I'll write it down here, pip 3 install numpy. Okay, and then write that in your terminal, hit enter, and then after that you'll have numpy. But assuming you're all biologists, you should probably have numpy already. And what we're going to do is we're just going to use this to initialize our matrix with all zeros. So we're going to make this zeros of the category M plus 1, N plus 1. So of the shape M plus 1 by N plus 1. And we need it plus 1 because we have one extra entry on each column for where we have no alignment. And we need an extra entry for that because we're going to actually initialize those gap costs here. Okay, and then we have path matrix equals np dot zeros, and then it's the exact same thing, M plus 1, N plus 1. Great. Okay, for I in range 1 to M plus 1, what we're going to do is we're going to say the alignment matrix at I and 0 is equal to our self.gap cost times I. Okay, great. And then our our path matrix at I0 is equal to no, our path matrix is going to be equal to 2. And what we're going to do is we're going to assign a little sort of mechanism of backtracking here, where we're going to define our paths as a specific number. So 2 is going to mean go left, 1 is going to mean go up. And so because we're defining these on the edges of the matrix, if we're on this top part, we're always going to want to go left from here. And if we're on this bottom part, we're always going to want to go up. So I'm going to say that's equal to 2. Or we can make this even easier, and we could say that this is equal to, we'll just make it 2. We'll make it 2. Okay, and then we're going to define our down column. So j in range 1, comma n plus 1. Alignment matrix at 0, j is equal to gap cost times j, and our path matrix at 0, j is equal to 1, which is going to be our move up. And I guess a better way of representing this path sort of matrix definition is going to be where we have this will be 0, this will be 1, and then this will be 2, and then this will be our value x that we're actually backtracking from. So if we can go upward based on this, we'll be able to backtrack either up, diagonal, or sideways from any value x in the bottom right corner of the matrix. Okay, great. Now we actually get into scoring. So this is our really cool dynamic programming problem where we've set up this scoring, this alignment matrix that's going to solve our problem at any I from 1 to m, and then any j from 1 to n. And that's going to fill in our entire matrix. So for I in range 1 and m plus 1, for j in range 1 and n plus 1. Okay. Species 1 is going to be equal to sequence 1 at I minus 1, because we're working in terms of our scoring matrix, not our sequence, and so we actually have to index 1 less for our sequence. And then species 2 is equal to sequence 2 at j minus 1. Okay, and I realized something wrong here. We actually don't want to have these be self.sequence because we are putting them in as arguments. Okay, great. Our diagonal score is equal to our scoring matrix. Actually, I should explain this. So our diagonal score is going to be our score if we go down the diagonal. So from here to x, if we're choosing both elements, and that's going to be equal to the cost of changing an amino acid or of keeping it similar between our two sequences at whatever ij point we're at. So we're going to say our alignment matrix at I minus 1 j minus 1, because we're backtracking one diagonal space, and we're going to say plus our self dot scoring matrix at species 1 species 2. Okay, cool. So that's just adding our cost from our scoring matrix to whatever our previous score was going diagonally. Okay, now let's define our right movement score. Right score is going to be equal to our alignment matrix at I minus 1 j. Okay, because we are not moving in both directions. We are only moving in one direction. We say self dot scoring. Actually, we're just going to make this self dot gap cost because we are taking a gap here, right? And we're going to do the exact same thing on this next line, and this is going to be our left score, where we go j minus 1 plus our gap cost. Okay, so our score overall is going to be equal to the maximum of our diagonal score and the maximum of our right score and left score. Okay, so this just gives us our score, and it's going to be equal to the maximum amount because we want to be progressing in our score. We want to find the maximum scoring alignment. Okay, and so using this array representation up here, what we're going to do is we're going to catalog that score, and we're going to catalog our path in the score matrix and in the path matrix and the alignment matrix. So we already know our score, so we're just going to say alignment matrix at ij is equal to score. Okay, cool. And then we're going to say if score is equal to our diagonal score. So we're going to slightly preference going diagonally if we have an equal scoring. We're going to say our path matrix at ij is equal to 0. Else if our score, actually in Python it's elif, score equals, I'm going to say, oh, I'm sorry, this isn't left score. This is down score, because we're going either right from here, or we're going down in any case, or we're going diagonal, but our diagonal score is easy. So we're going to say if this is equal to down score, path matrix at ij is equal to 1. Okay, and then else, which is going to be our only other option, we're going to say path matrix at ij is equal to 2. All right, and that's it. And that's it, because we're solving this problem for every I and j, and so by the end of it, we have a fully scored matrix. We have a fully scored alignment matrix. So all there really is after that to do is going to be to return the alignment matrix and the path matrix as a kind of Python tuple, but we don't really need these parentheses. We're just going to return it. Okay, so we have our two return values. We have our alignment matrix and we have our path matrix. Okay, awesome. Now we are going to actually let's test this. Let's make sure that we're actually doing this correctly. So we can say we have our alignment and we have align dot run Needleman Wunsch. Okay. Yeah, I'm not sure why it's not loading that. And then we're going to sequence 1 and sequence 2. Okay, and we'll just print this for good measure. It's going to be massive, but as long as it's initialized with scores and then our path matrix is initialized with other stuff, it'll be going great. So we do have a problem. It's because we did this left score, down score kind of mix up here. So we're going to find left score. Yeah, and we're just going to say that's going to be equal to down score. Cool. Great. So that ran pretty fast. And what it shows is this is our path matrix because it was second in our return value. This is our path matrix, and it's a lot of 2s, 0s, and 1s determining which direction we should go from any point in the matrix. And if we go back, we actually see our scores, so we're getting some positive alignments. And then in the bottom right, we have our maximum score. We have our maximum score of 56. And so we're going to be able to backtrack using that and kind of find our alignment path. So that is super cool, and we want to preserve both of these matrices because we need the maximum score from both of them. And so what we're going to do now is we're going to write our little alignment helper. So our alignment helper is going to run Needleman-Wunsch for us. Our alignment helper is going to say our alignment matrix and our path matrix, okay, is going to be equal to self.run Needleman-Wunsch, and then with sequence 1 and sequence 2 that we gave it. Okay, now we have our alignment matrix and our path matrix, so that is fantastic. The next thing that we're going to want to do is get the maximum score from this alignment, because we want to show our maximum score from our alignment. So we're going to say alignment matrix at its maximum score. So let's just say alignment score is equal to alignment matrix at -1, -1, and this is just a little Python trick to go backwards in array elements. So if you start at 0, you can actually go backwards by hitting -1. Python matrix or Python arrays kind of perform like they are circular in a way. And then we're also just going to return our path matrix. So return. Great. Okay. And that's all we really need. And now we're going to do this. We actually don't want alignment. Make sure you want alignment score. Okay. And this is yeah, our alignment score and our path matrix. Cool. We're going to test that really quick. And the reason I put an underscore first is because in Python functions, what you want to really do is you want to not call functions with an underscore in front of them. They're technically private, but Python doesn't have a concept of private and public functions, so it's more in the nomenclature than everything. So we're going to get get alignment helper of sequence 1 and sequence 2. And we're just going to see if that score comes up first for our alignment. So we don't want that. We want to see, yep, there it is, 56. That is exactly what we wanted to see. And then we have our path matrix. So the next thing that we want to do is this path matrix really doesn't matter except for when we're returning the alignment itself. So we're going to write our path interpreter in the get alignment method. And so now we're going to run this, we're going to write this path interpreter. And what we're going to do is we're going to backtrace using that path matrix that we just made. We're going to build this alignment string based on this kind of this matching string pattern of just these little bars between matching amino acids to make it easier to read. And then we're also going to return the maximum score below it. So easiest way to do this is just going to say align top equals nothing. There are matches equals nothing, and our align bottom equals nothing. Wonderful. So our max scoring, right. We're going to start from the back of the matrix actually and work our way toward the top left. So we're going from bottom right to top left because bottom right is going to always be where our maximum alignment score is. And we're going to have to work backward toward the beginning. So we're going to start at I equals our length of sequence 1 minus 1, and then j equals length of sequence 2 minus 1. Okay, and then while ij is not equal to -1, -1, what we're going to do is we're going to backtrace. We're going to say our path is equal to our path matrix. Right. We have to actually run our alignment first to be able to do this. So we're going to say our score and path matrix equals self dot alignment helper of sequence 1, sequence 2. Okay, so now we have our score and we have our path. That's great. Yeah, we're going to say path equals path matrix at I plus 1, j plus 1, and indexing is always kind of difficult on backtracing, but we're going to say species 1 is equal to our sequence 1 at I, and our species 2 is equal to sequence 2 at j. Great. And our match is equal to that. Okay, so if, and this is the tricky part of actually building these paths, if our path is equal to 0, we update all three of these accordingly. We do I minus 1, we do j minus 1, we do if species 1 equals species 2, match equals this little pipe here. Yeah, okay, whatever. Editor's taking a second to catch up. Else, if our path is equal to 1, then we know that we're going upward. We're going up in the matrix. So species 1 equals this. And we're only going to subtract from j. Else, we know that we're going left in our matrix, and so species 2 equals this dash. and that's going to be our gap in species 2, and I minus equals 1 because we're going left. Now, after all this, we're going to update everything, and we're going to say align 1, or the align top is going to be equal to species 1 plus align 1, or align top. Okay, and align bottom equals species 2 plus align bottom. And then our matches equals matches plus, right, it's going to be our match plus matches. All right. And so this is going to kind of build up our alignment as we go. And the value we're actually going to return is going to be comprised of these. We're going to say format string in Python, align top, new line, matches, new line, and then align bottom, new line, score, score. Yeah, and that is going to be it. That is going to be it. So we're going to just go through. Let's just try running this again. And we do need to change this alignment to print aligned at get alignment between these two sequences. And that's it. We have a successful alignment between our two example sequences right here. And it's just as simple as that. It's using this breakdown of our problem to split this into smaller problems and find where these sequences align best. So let's try this on a real example. I've downloaded a human hemoglobin beta subunit, a pufferfish hemoglobin beta subunit, and then a plant, I'm not even sure how to pronounce this, leg hemoglobin 1, which is also useful for plants transporting oxygen. Okay, so let's see what happens when we change up our alignments to actually show something kind of useful, kind of interesting. Human hbb.fasta, and let's just align this with pufferfish first. Puffer hbb.fasta. Oh, and our service is broken. Okay, so here's what's going on. It's annoyed that we have tried to split this based on just one line, where in reality FASTA files are multiple lines, but we're going to kind of hack around that. I'll leave it up to you to actually fix that, and the fix is just going to be making sure that it's going to be similar to the Blossom 2 data thing here, where we ignored the first line and then we concatenated all of the other lines. So you can go through that. But what I'm going to do for this little example right here is I'm just going to be lazy, and I'm going to subtract. Yeah, I'm just going to take away these new lines. I'm going to put it all on one line. I'm going to do the same thing for our P and for the puffer, and the puffer apparently doesn't exist. So what we're going to go back is go here. Yeah, here it is, the fugu pufferfish, the very, very poisonous one. And we're going to see how much we relate to a pufferfish. You know, keep in your mind whether you think that's a lot, a little, or, you know, whatever you may think. Turns out it's a good bit. Look how similar we are to pufferfish hemoglobin. And that's no coincidence. That's because in all sort of living creatures, hemoglobin is a very highly preserved protein because it's so important for transporting oxygen. And we can get data like this in just a second now, because we've coded this algorithm in a very optimized way. So now let's try comparing ourselves against a plant, P LHB, FASTA. And it says invalid sequence path. Yeah. Okay. LHB. There we go. Yeah. And so you can see even in the plant, we get, you know, not a great alignment score, 36 versus 353. Um, but there's still similarities. We have lots more gaps, and we still do have some similarities between plant and human because plants transporting oxygen is still a very vital process of their metabolism. They have to transport oxygen out. It is a waste product of their metabolism. So that concludes it for now. And in the next episode, we're going to be showing exactly how significant these alignments are, doing a very, very simple trick. But until then, I'll see you. Good, best of luck coding new things, and congratulations on coding your very own sequence alignment tool.